We're still on chapter 3, right? So we are now working on measures of variation, right? So measures of variation included range, right? So variation tells you, we started, right? The easier part was measures of center, right? That told us, okay, where's the center? Mean, median, mode, right? You've already probably know a lot about that, right? So range is one measure of variation, right? It's just what's the difference between the largest piece of data and the smallest. It's not the best measurement because it's obviously very not resistant at all to outliers, right? So instead, you want to, and it only depends on the smallest and largest piece of data, right? So instead, we use something called the standard deviation, right? Which is a little bit harder to calculate. I went over an example of a calculation, but let me tell you a little bit about this, right? So here's the formula for standard deviation, right? Where X bar is the mean. So each piece of data, you subtract the mean from it and you square it. You sum all those together. You divide by the number of pieces of data by 1, and that gives you the sample standard deviation. If you're calculating the standard deviation of a population, you use n instead of n minus 1. So standard deviation tells you, right, how much on average, kind of, even though average isn't this, it's roughly telling you, right, how much do numbers vary away from the mean. And because it uses, when you square numbers, right, they become positive, right? So that's actually a good thing. If you think about it, if this formula didn't have that square in there, right? When you're looking at data being varied, you don't want, right? There's a joke, right? Once, a statistician, one person, 3 people go hunting, one person misses the target to the left, the other one misses to the right, the third one says I hit it, right? That's not how things work, right? But if the square weren't here, right, one person's -2, right? The other is one's 2 less than the mean, the other's 2 greater than the mean, add them together, you would get 0, right? Which would say there's no variation. So squaring that fixes that, right? It makes that all the variations have to be positive, right? So larger values of S indicate greater amounts of variation, right? S can increase dramatically with outliers, but that's kind of okay because outliers do mean that your data does vary. It doesn't, so we wouldn't want it to be completely outlier resistant, right? That would be bad because outliers means variation, and variation should be measured by standard deviation. Standard deviation is always measured in the same units as your data values. And it's a bias estimator, which we'll talk a lot about this later, right? But what roughly that means is that, okay, so we'll spend a lot of time talking about this later, but just roughly, right? So something that's not a bias estimator is the mean. So if I took different samples of a population, right? I took random samples of 30 people, right? And I took the mean height of theirs. Sometimes that mean height would be larger than the mean height of everybody in the world. Sometimes it'd be smaller, right? But I've looked at all the groups and looked at all those sample means. The real mean of the whole population would be in the middle. This is not true about standard deviation, so that's called a bias estimator. Again, this is something that you will learn a lot about later, but I'm just kind of introducing you to it now. Okay, so in calculating the standard deviation, I showed an example, right? You might have it in your notes, but I want you to do the same thing without looking at it now, right? To just kind of calculate it, and then we'll kind of try to go over it, all right? So this is the procedure for finding your standard deviation, right? So first, you need to find the mean of all of your scores, right? Or whatever it is. So you need to find the mean because that's your X bar. See, you never can really get the temperature right in here. It's always too hot, but then when you open the window in the winter, it gets too cold, right? So you just have to keep closing it and opening it repeatedly until, I don't know. So first, you get the mean. Then once you have the mean, it's really easy to find these differences, right? Just for each value. So here I'm just imagining my first value is 3. I have a value of 0, some other values, right? Okay, if my mean is 2, right, I would subtract 2 from 3 to get 1, right? Subtract 2 from 0 to get -2. Then I would square each of these in this column. Then you're going to sum up this final column. That gives you the numerator of this term. Divide that bad boy by n minus 1. Take the square root. And you are done. Obviously, statisticians rarely calculate, I'm going to say rarely, the answer is probably almost never calculate standard deviation by hand, right? Oh, sorry. But we want you to be able to do that just so you can get a sense of what this formula means. If I just tell you how to calculate it on your calculator, which I will tell you how to do, right, you just completely lose a sense of what it is, right? At least doing it gives you a sense of what it is. So it's going to be something that we do like once, right? I will assess you on it once, but then mostly just because it takes a long time and it's very error prone, you're mostly going to use technology to do this, okay? Yes, Bobby.
Second column is the one that is the x in the equation.
The second column is x minus, is in each data piece how much different it is from the mean, right? So in this case, right, if the mean is 2, right, and the data piece is 3, you do 3 minus 2, which is 1. Okay, so working with the people around you using your calculator too, I want you to calculate Dan's standard deviation, and this is the formula you're going to use, right? So just follow the procedure that was on the previous slide, right? Work with the people around you. We actually did this before, so you might have the answer, but I just want you to practice this. You can do this on your own with the people around you, but then we will check in and I'll kind of walk around, all right? I'll flip back to the other slide, but I just want you to have time to copy down the data values that belong to Dan, all right? Over this one, right? So I did the work here, right? So first, right, I mean, you wouldn't need to write this down. I expect you can easily find the mean, right, just by hand. But so you find the mean, that's 74%, right? Then you, right, for each score, you subtract, right, to get the differences. Some of these are positive, some will always be negative, right? Because some scores are above his mean, some are below it, right? That's how you create this first column. And again, I wouldn't expect you to write like this table you'd want to write out, but obviously things that you're adding up, you can just do them in the calculator without writing it down. I'm just showing it, right? So then you can use the formula, right? You square these, right? They all should be positive, right? You should never get a negative number when you square, right? And then you add them together, right? This is the sum. You divide this by 5. You take the square root of that, right? Make sure you do that in order, right? And you get 23, right? So since that's 23, right, that's 23%, right? Or 23 points, however you want to think of these scores. It's in the same thing. It's in the same measurement, right? So if I'm taking the height, if I want to find the standard deviation of our heights, right? If my original heights are in inches, standard deviation will be in inches. If my original height's in centimeters, the standard deviation will be in centimeters. Yeah, question, Mars. N minus 1. For a sample, you want to do n minus 1. If it was a population, so like, I guess this is some of Dan's tests. If it was the population, you do n. The reason why that is kind of mysterious, right? So you do n minus 1, right? Now, typically, it doesn't change too much. So this is like something that you use n when you should have used n minus 1 or vice versa. That's like a 1 out of 10 points type mistake, right? Not a huge deal because, and then obviously with large samples, the difference is minute. Other questions on how this calculation was done? It's not, you just follow the procedure. There shouldn't be any, problems. It's just something that takes a while to learn how to do. Because the square root on your calculator is in a particular place. This is just something you will be asked to do this on this celebration next week, and that'll be the last time I'll ask you to do it. I won't be asked you to do it again on the final or whatever, because this is just, I'm kind of hazing you just a little bit, right? Because there's a much easier way to do this, but if I just told you how to get off your calculator, you would forget about what the standard, because this really does show you, right? It's taking the mean, right, of your differences, right? You have a whole bunch of differences squared, and then you're finding the mean of it. Okay, so let's notice something here. So here's Dan and there's Barb, right? How would you, so neither student seems to be like doing much better than the other one, but what do you notice is the difference between Dan's and Barb's scores? They're actually gonna have the exact same average, although we don't use the word average, right? We use the word mean score. But what is the difference between Dan's and Barb's? Yeah. Yes, so what we call that is that data set has a larger, they have the same center, right? But Dan's has more variation, right? Which the standard deviation is a measure of. So would we expect Barb's standard deviation to be bigger or smaller? Smaller, right? Because you can see when we do all these sorts of calculations, right? These differences will be smaller, right? But instead of doing it over again, let's learn how to use our calculator to do this, right? There are ways you can do this on Excel. There are different tools, but I'm just going to show you right now how to use the graphing calculator to do this, which you do need for this class, right? Yeah, if you can buy them. So they're quite expensive to buy new on Amazon or eBay. Getting them used could be like significantly less because they've been around for like 20 years, right? You can, a TI-83 manufactured in 2001 would totally be sufficient for this class. So let's turn on the document camera so you can see. Okay, it's a little hazy, but that should be all right. Okay. So you're going to hit, if you have something already in there, let's just do second memory. Clear all lists in case you have something in there already. Then let's go to stat. You go to edit, right? You hit enter. This allows you to enter in the data, right? So then you have to input your value. So let's input Barb's, which is 73. Enter. 75, enter. 76, enter. 72, enter. 70, enter. 78, enter. Okay. Then you're going to go second quit. You go to stat, go over to calc, just hit one variable statistics. Everything's in L1, so we don't need to specify L1. If we did, you would need to do something there. But let's hit enter here. Notice it gives us some different pieces of information, right? Notice it says, first it says X bar is 74. That means the mean is 74, right? This, we don't need to necessarily use these, but they're there, right? So this is the sum of all the data values. This is the sum of all the data values squared. But here's the important one. This S with the little X on it, that is our standard deviation. So it is much faster to do it automatically with your calculator. Notice this is the standard deviation using n instead of n-1, the little sigma one. Now notice it also says you have 6 values. It also tells you the minimum, the maximum, the median, and Q1 and Q3. I will teach you today what Q1 and Q3 mean. But this gives you basically everything you would need to know about a set of data. Everyone follow that? Does anyone need to see me? Yes, question. Sure. All right, were you able to get Okay, all right. So you have a different calculator. I might not know exactly, but in mine, you hit stat, right? Next to calc, you move from edit to calc, you hit enter, it will give you the statistics. If you have a completely different calculator, you can Google it. And if your calculator doesn't do it, sorry, right? But you'll need one of these. I do have, there's some extras, but like there's not enough for every class to have extras. So I don't know how that will work, but try to have one for the celebration next week. Any other questions? Yeah, Bobby.
So for the, and I don't know, do we need to know that symbol of the n? Does n equal 6?
That is sigma. Oh, n. Okay, so that's sigma. That is the that's population standard deviation. And I did mention that last week. So that's where you would divide. So notice that's smaller. So it's dividing by n there instead of n minus 1 in the square root form in the formula that we just used.
Standard population.
So that's for population, right? So if you know that the set of values you're taking the standard deviation represents an entire population, you would use sigma instead of S. We're going to talk a little bit about sample versus population because that's one of the questions most of you missed on the small celebration. So in this case, so for Dan, his mean was 74, and his standard deviation was 23. Barb, same mean. The standard deviation is what we calculate on our calculator. So let's do it to 1 decimal. So that was 2.9. So her scores are much more consistent than Dan's, which is what standard deviation tells you, right? The larger the standard deviation, the more your values vary. Questions? So mostly you're just going to use technology to calculate standard deviation if we need to, but we're going to do it by hand at least once. So let's talk a little bit more about understanding standard deviation, right? So one of the things we talked about is some of the different ways, like normal, skewed, right? So most values have that roughly bell-shaped curve, right? And we'll talk more about, there's be a whole unit on that. But since that's most data, when you have something that is normal, right, there is something called the range rule of thumb, right? So what it tells you is that the vast majority of data will be within 2 standard deviations of the mean, right? So this is where 95% of your data should be. Only 5%, roughly, is significantly high or significantly low. So let me just, this number is probably not correct. But let's just say in the mean, so let's just think about this for height, right? So roughly, let's say that the mean height is, for men, let's say that that's 5'9". Let's say the standard deviation is 2 inches. Okay, so I take that 5'9". All right, add twice the 2 inches, do the same with the minus. We'll do another example of this, right? So if I double those 2 inches, that's 4 inches, right? Add it to 5'9", that is 6'1". I'm just making these numbers up. I don't know if this is true, right? This is 5'5". This is saying, right, okay, based on the range rule of thumb, right, 95% of men would be between the heights of 5'5" and 6'1". And that seems roughly accurate to me, right? So according to this also, if a man is taller than 6'1", his value, right, is considered significantly high, right? That means like it's different in a statistically interesting way, right? Because it's it's higher than the vast majority of people, right? And if a man is lower than 5'5" in this case, his height would be considered significantly low. Yeah, the mu, yeah. It's not an M, that's the Greek letter mu. Yeah, that means population mean as opposed to X bar, which means sample mean. Population mean, and then the thing that looks like a cannon is sigma, which is population standard deviation, right? I believe I had that on a slide the other day. So just think about how useful this is. Yeah. Right? That's sigma. That's the lowercase sigma, right? It sounds like S, so it's the Greek version of S, so that just means population standard deviation as opposed to. So that means the standard deviation of a whole population, right? As opposed to, a sample. What was I going to say? Notice this is useful, right? It allows you, if you know, like there's, let's say a topic you don't know anything about, right? Like I don't know anything about the average amount of water used by a house. It's just not something I think a ton about, right? If someone gives me the mean, someone gives me the standard deviation, that's enough for me to know, right? If your house uses a significantly large amount of water or significantly less than normal, because I can just see, is it between mean minus 2 standard deviations and mean plus 2? Yes. So you wouldn't really, okay, so it's kind of a hard question to answer. So if you have the sample, right? The sample, you would have access to the whole sample, right? So you would know exactly where it fits in the sample. Like you would know whether you're the, like, within this sample, right, you would know if you're the second tallest, third shortest, whatever you are compared to everybody else, right? The population's harder to find out. So you would use it for population, but I suppose you could use it for the sample. Assuming the sample is collected in a representative way, like it's randomly collected. Rough, we'll get to that later. It's normally true. And most of it, and this is a rule of thumb, right? So rule of thumb means it's not always true. It's true for most situations, because most situations follow something called the normal distribution, which is chapter 5, right? So we'll learn about what situations this follows. This rule might not be true for things where this is not true for data that you know is highly, this is not true for data that's highly skewed, right? So imagine something, so like net worth of individuals, right? There are, so things that vary, like that can have, so net worth of individuals has a very long tail on the right, because there are people who are worth, right? They say, like, if you look at Elon Musk, like net worth, like what he earns in like 10 minutes is more than like all of us could possibly earn working if we could somehow like earn $1 million a day for our whole lives, right? It's still not going to be that amount, right? So for things that are like that, not so much. Okay, so notice if 95% of the values are in this 2 sigma to the left, 2 sigma to the right, right? If your data set is not very large, right, you can get this. So this is also a rule of thumb. This rule of thumb is even weaker, right? Ms. Mars, good job on asking about it, than the one we had on the previous page, right? It's saying, right, if you want to estimate a standard deviation, and all you have is the range, the standard deviation of a set of data is roughly a quarter of the range. And what that's basically assuming is this. I did come from that, okay. All right, why is it? Oh, these slides are in here twice for some reason. Don't know why. Okay. This just comes from this, right? If your data set is large, is not very large, right? It's small. You should expect to not have any data, right, in here. Right? Only 5% of the data is in there. So let's say you only have 10 pieces of data. You would expect nothing to be in the green region. You kind of following what I'm saying? Because little of it is, right? So this would be all of your data. And notice from the mean, it's 2 standard deviations up, 2 down, right? So what I'm doing is I'm explaining the origin of this rule. I will not assess you on it, but if you just want to kind of, right, it can help you remember it or understand it, right? This width of this yellow rectangle is 4 times the standard deviation, right? So if you don't have any values that are significantly high or significantly low, right, this distance right here would be your range, and it should be 4 standard deviations, right? So divide this bad boy by 4, you'll get roughly S, right? This works best for a small data set. For a large data set, this is less likely, this is more likely to have an error. But also too small, right? So this is roughly good for a medium-sized data set. Notice this is so rough that even though it's a rule of thumb, they did approximate, right? So this could totally be wrong. But if you got nothing else, go ahead and use it. Also, right, if you calculate, right, if you don't have your calculator, you calculate a standard deviation and it's way different than 1/4 of your range, probably made a mistake. So what do we have here? These slides are so weird in that order. Okay, we'll get to that in a second. So I would use both of those rules. So here's the standard deviation. We talked a little bit about this. I forgot that I hadn't mentioned this because it's been a while, right? So this is what you asked about, Bobby, in the calculator. The symbol underneath the SX is sigma x. So if you are calculating the standard deviation of a population, instead of dividing by n-1, you divide by capital N, where n is how many are in the entire population. That's really the only difference. And you can kind of, and this is the thing, you kind of want to read the question to figure it out, right? Right, like if it's a story, right? Like if it said if it said Dan, and Barb have exactly in this, in their statistics class, they're taking 6 exams, here are their scores, I would have used 6 instead of 5 because I would have known that's all of their scores, right? But here it said it was a sample, it was some of their scores. So really, only thing you need to understand, population, n, not n-1. And it uses this symbol, which is pronounced sigma. Okay. That's all you need to get out of this. That's what I would write down in my notes. Population, n, not n-1. What is the variance? The variance is just the standard deviation squared. That's it. So if you're calculating it by hand, remember the last step that we did, right? When I had you do that exercise by hand was to take the square root, right? You got that sum, you divided by 5, then you took the square root. To get the variance, just don't use that last step where you take the square root. Or if you have the standard deviation, just square it, multiply it by itself. Pretty straightforward. We don't need to use new symbols for variance, right? Because it's the standard deviation squared. So we just represent standard deviation squared by literally writing the symbol for standard deviation with an exponent of 2. That's pretty sweet, right? You don't need to. So I know you guys are probably irritated by how much new notation you have to memorize. This is one where you don't, right? Because you just know, right? Hey, if my population standard deviation is 3, my population variance is 9. It has kind of, because it's, you know, the variance and standard deviation, if you know one, you know the other one. One's just the other one squared. They're very similar. It has the same properties. The only thing that's kind of weird is that the units of variance. So if I measured the height of everybody in this class, all right, the variance might be 9 square inches. Which is weird, right? If I asked you guys how many dogs each of you have at home, and I calculated the variance of the number of dogs you guys have, the unit for the variance would be dogs squared. What the hell does that mean? No idea, right? But that's the unit. It has to be, right? Because when you square it, you would get dogs. So standard deviation is much more convenient of a measurement than variance typically. But variance has the advantage of being an unbiased estimator. We will get to what that means in a later unit. Just understand that unbiased means better. Which I guess you could guess. Bias sounds bad, right? Yes. Yeah, if you're fine. Yeah, at the end. Or if you already have the standard deviation, square it to get the variance, right? If you have the variance and you need the standard deviation, take the square root, right? Okay, so remember what I said earlier about the plus or minus 2 standard deviations, that's where 95% of the data is? Okay, so that comes from a specific rule that we call the empirical rule. This is only true for normal data, but so normal data, roughly right now, just take normal to mean bell-shaped. This is normal with a capital N, not lowercase n, right? Normal data means a particular type of data. It doesn't just mean data that's not strange. Box plots. I don't think it's going to take as long. Okay. So here's the thing to understand, right? This picture roughly tells you it, right? So normal data, right, is symmetric, right? So you would expect half the time you're below the mean, half the time you're above the mean, right? The empirical rule says roughly 68% of the time, and these numbers seem very strange, right? You're gonna find out where they come from later. You have a whole chapter on this. 68% of the time, you will vary then less than 1 standard deviation, okay? So, right, if the standard deviation is 2 inches, right, in height, that means 68% of the time people would be between 68% of every person alive is within 2 inches beneath the mean and above the mean, right? Very few. So 95% is within 2 standard deviations of the mean, right? And 99.7, basically everybody, is within 3 standard deviations of the mean. So IQ is pretty much discredited, right, as a measure of intelligence, but let's just use this as an example because the IQ test is a standardized test. So it's designed, right? The test is normalized so that for every IQ test, the mean score is supposed to be a particular amount. Anyone know what the mean IQ is? No, I know what it is, but I'm just wondering. It's supposed to be 100 points. Right? So that is your average Joe has an IQ of 100. And the standard deviation is supposed to be 15 points. Okay, so that means the middle 68% of people would have an IQ between 85 and 115. Right? Do you see how I got the 85 and the 115? I added the standard deviation to the mean and I subtracted it. 95% would have an IQ between 60, 70 and 130. 99.7% of people would have an IQ between 55 and 145. That's what the empirical rule says. Yes.
Well, this could also be for population.
It should be for either, but yeah, so this is roughly, I don't know why they use, so you should think this is the population, right? And the sample should have a distribution like the population if it's corrected in an unbiased way, right? Like a convenience, right? Like a sample should be like the population, assuming that it's not collected in a way that is assuming it's one, it's large enough, and we'll be able to calculate that later, and two, that it's collected appropriately, right? If you randomly sample people walking out of NASA, are you going to get a distribution like this? No, because like you're going to be oversampling people with high IQs, something like that, right? So assuming that it should be the same for either, assuming your sample is collected appropriately. It will always apply to a population. It will apply to most populations, right? And it will apply, and if it applies to the population, it should apply to a sample given one that it's large enough to it's collected correctly. So here is an example. All right, so let's look at this one, right? So, and we'll take a break in a little bit. Mean body temperatures, right? Some people have a body temperature that's much, right? So some of what they say, right? Maybe you know somebody, right? Like they say, oh, if you have a temperature over 100, you have a fever, right? My mom has an abnormally low body temperature. If her temperature is over 100, we should probably call 911, right? Because of that. Some people run hot, I guess, right? So, but it doesn't vary very much. So the mean, right? And this is, notice it's talking about all people. So is this a population or a sample here? It is a population because it's not talking about some. It's saying, it says body temperatures of healthy adults. So that means everybody, right? So your mu is, so this tells you where the center of it is, right? If you're an alien without knowing the standard deviation, you wouldn't be able to say much about body temperature, right? This is telling you, this is a pretty small number, right? Compared to the mean. This tells you that, you know, there aren't people running around who have a mean body temperature of 85 degrees. That's not a thing. Okay, so A does not require any math. So within one standard deviation of the mean, What percentage of people from the last slide are within 1 standard deviation of the mean? It's literally just written down. Within 1 standard deviation of the mean is what percentage of the population? 68. So same thing for this population, 68%. Now, just for fun, we can figure out what 2 body temperatures those are, right? So 68% is within 1 standard deviation, right? So the mean is 28.2. Standard deviation is there, so you can do I did this ahead of time. Oh, I have these backwards. Yeah. So I just took the mean and added the standard deviation, right? Subtracted the standard deviation. Think of the standard deviation as a rule, as a ruler to tell you how different you are, right? So some things vary more than other things, right? So that's why I want the standard deviation, right? So what we're saying is that 68%, right, of adults, assuming that they're not sick, in which case they would have a different body temperature, right, will have their resting body temperature between 97.58 and 98.82. That is not 68% of the adults. Now, to figure out this one, we'll just figure, we'll give you this formula that I'm using here later, but I'm just going to kind of give you intuition for it. So to figure out what percentage of people have a body temperature in between these 2 temperatures, we need to figure out how many standard deviations are they away from the mean, right? Because based on this, right, it tells us what percentage, right, based on standard deviation, correct? All right, so let's look at the 100. That is universally what they say is like a fever, right? So if your body temperature is normally at 100, that's way above average, we would assume, right? So let's subtract. Let's just try to think about what this says. So suppose you have a friend, they're, I guess, a weird, a strange biological specimen. Let's say something like that, right? Their average body temperature is 100.06 degrees, right? You might say, that is hot, right? So to get an idea of how hot that is, you say, let's subtract the mean from your body temperature. Strange person who's always warm all the time, right? I get 1.86 degrees, right? That tells you how much hotter they are than average, right? That doesn't sound a lot, but it is a lot when you consider that the standard deviation is 0.62, right? So this is the difference, right? Think of a standard deviation as like a ruler, right? We want to figure out how many standard deviations fit in here, right? The more standard deviations that fit in a difference, the stranger the difference is, right? Well, you'll later learn as we're calculating something very specific. So you divide that out, you get 3. So that's 3 standard deviations. That's STD. If you're going to laugh at that, let's get that out of the way. 3 STDs above the mean. This other one, if you do the same calculation, this person is colder than average. So you get a negative number. You get 3 below the mean. So this is a z-score. I will go over in detail in the second half of this class how to do this calculation, all right? So don't worry too much on it if you didn't follow it, but roughly get the idea. You're dividing the difference by the standard deviation. Okay, so one of these temperatures is 3 standard deviations above the mean, the other is 3 below. So based on the previous slide, what percentage of people? 99.7. So almost everybody. Which is good because, right, if there's somebody out there, there's only a tiny percentage of people out there whose average body temperature is above 100 degrees, right? So imagine how difficult that might make your life. Every time you go to the doctor, they're going to think you're sick, right? It would be very difficult to actually know how sick you really are, right? Every time you have any fever, people would basically think that you're dying. Remember when I was about your age, my sophomore year of college, I had a fever of 103 degrees. That was not fun.